we are still discussing longitudinal stick fixed static stability of a conventional airplane, right. We said that we will now look at a conventional airplane where we will have wing which will be positively cambered and a tail behind the wing. Okay, with reference to this picture, and after making some assumptions based on some distances which were small, and and that this tail is lying in the wake of the wing, right. So, there is a downwards angle, or I would rather say tail is lying behind the wing, okay, and because of that there is a change in this velocity vector, right, not only in the magnitude, but also is the angle it changed, right. So, angle of attack that a tail will see is right, and alpha FRL is alpha W minus IW. We also said that this epsilon has two components, right. So, downwards angle itself is changing with angle of attack of the wing, right, plus this epsilon when the wing is at 0 angle of attack. Okay. So, coming down to what we achieved by adding a tail, we found that the tail not only adds to the Cm naught, which I am calling this as Cm naught due to tail, not only adding to Cm naught, but also to the tail, to Cm alpha of the total airplane, and Cm alpha due to the tail, expression for that is right. We did this in the last class. So, now the total Cm naught of the wing tail combination is going to be sum of the tail contribution, right, and the wing contribution, right, and Cm alpha, the new Cm alpha of the wing tail combination is sum of the wing contribution and the tail contribution, right. Okay. So, if you want to look at it graphically, what is happening is this. This was the wing alone contribution to the Cm alpha curve, right. The tail alone contribution may be something like this, right. And this is has to be positive, right. So, finally, for this wing tail airplane configuration, what you would get is something like this, right. Wing plus tail. Anything else which is also important in contributing to this, to these quantities? Do you have anything else on the airplane which may contribute to pitch stability or Cm naught? You have fuselage. Anything else? Power plant. Fuselage contribution to Cm alpha is usually destabilizing. I will cover that aspect in the next lecture, and power effects are actually very prominent, okay. That also we will discuss with respect to what kind of power plant you have, right. You can have jet engines, you can have turboprops, right. So, we will look at all that in the next lectures. Cm, yes, right. Thanks. Okay. So, we are going to discuss these two in detail, okay. But in this class we are going to do a problem, okay, example problem. Okay, there is this high wing single engine general aviation airplane. Okay. And this example we have taken from the book by R.C. Nelson. Okay. So, number I think is 2.1. Okay. What we have been given is CMCG for wing fuselage combination, okay, and that is this alpha is alpha FRL. Okay. Other data which we will need are these. This C bar is the mean aerodynamic chord of the wing. So, wherever you see this W subscript is for the wing. Okay. CL alpha for wing fuselage combination. So, clearly the wing is positively cambered, right. CL at alpha 0 is 0.26 yeah, 0.26, which is for the positively cambered wing. Now, the problem is to estimate right. Now we have seen here we have to, or we can adjust the parameters in VH. VH is tail volume ratio, right. After we have fixed the wing, to change this VH we can only play with ST or LT, right, and the tail setting. Okay. Other parameters that are given are these. So, assuming tail efficiency to be 1, so from this data, which is the lift curve slope of the tail, is clear that the tail is what? It's a symmetric airfoil, right, consisting of symmetric airfoil. So you can back calculate and you will find that this is for the symmetric airfoil. All right. How do you decide on LT? Now, LT will depend upon lot of things, right. First of all, the tail has to produce enough moment, right, to trim the aircraft. That is one condition, and this is also going to affect the stability through this term, right. So, right, and it's also going to be affected by what is the overall length of your aircraft, right. Once you have placed your wing at some location, you only have only so much space left where you can place your tail. All right. So, let us look at this problem. We want to estimate the horizontal tail area and tail incidence angle IT, so that final CMCG, okay, of wing fuselage tail contribution is this, right. How do you go about it? All I need to do is find out what is the tail contribution, right, and that I can obtain by subtracting this from this, isn't it. This is for the wing fuselage tail combination, this is for wing fuselage combination. Now I can find out what is Cm alpha due to tail by subtracting 1 from 2, right. This is not Cm alpha, but okay. right. So, you have Cm naught tail, which is what is Cm alpha tail?
Minus.
So, again this minus this, right. And this is per degree. Okay. So, this should be equal to minus AT is the lift curve slope of the tail, is also CL alpha tail. And before you can do that, you have to convert this to per radian, right. So, you have to multiply this by a factor which is this, right. So, what all you know? You know this, right? Lift curve slope of the tail is given here, right? You know LT inside this, right? Let's look at what all you know. So, you know this quantity LT, right? Only ST is an unknown here. In the second equation, you do not know about this, right, and you also do not know about what is epsilon naught, right. IW is given. Okay. So, let us try to find out what is epsilon naught and what is d epsilon over d alpha. So, there is a simple relation between epsilon, this downwash angle, and the lift coefficient of the wing. So, there is a relation which is between downwash angle, lift coefficient of the wing and the aspect ratio of the wing. and right, it's like this. So, I want to find out what is epsilon naught and what is this derivative, right. So, epsilon naught is nothing but right. The lift contribution is mainly coming from the wing, right, and not and very less coming from the fuselage. So, therefore, we can take this as the total lift coefficient, right. So, in this of the wing, so here what we have been given is CL at alpha equal to 0 for the wing fuselage combination, right, but fuselage will not have. Similarly, here also this CL alpha which is given for wing plus fuselage combination will actually represent mainly the wing contribution, right. So, we can find out what this epsilon naught is using this expression for the okay. D epsilon over d alpha is nothing but the derivative of this with respect to alpha. So, 2 CL, right, because the downwash is mainly because of the wing, right, that is why we have this W here. Now, this is very close to this quantity what is given for the wing fuselage combination, and using that you can find out what is d epsilon over d alpha, and I am just writing it down here, you can find that is correct. Okay. Yeah, that you have to do anyway. Okay. Now, we have two equations. ST and IT, right, everything else is known. Right. So, using 3 and 4, you can find out the tail horizontal tail area, which is now this tail setting has to be negative, okay, if you want to achieve CMCG wing fuselage tail combination to be this, right. Is that clear? Okay. So, what we have found is from the given requirement on the aircraft in terms of the CMCG wing fuselage tail contribution and this CMCG wing fuselage contribution, the information on how to size your tail, right. Okay. There will be other requirements also, which we will talk about later when we come to talk about longitudinal controls. Okay. But let us look at something else now. Let us say this is the Cm versus alpha curve for your airplane. Right. Will this curve depend upon something? How will the slope change? So let us write down the expression for Cm naught again. This is Cm naught due to tail plus Cm naught due to wing, right, and Cm alpha. We are still talking about wing and tail combination. Okay. Cm alpha is Cm alpha tail plus Cm alpha wing, right. If I want to write the expression for this, what is Cm alpha due to wing is AW, which is CL alpha W. Okay. Right. This Cm alpha due to wing. Okay. Plus okay. So now we have wing plus tail in place on the airplane, right, and let us not bother about the power plant and the fuselage. Okay. What else can change this profile? Only wing plus tail configuration. We are not yet talking about controls. Okay. Just look at this formula. What is it that may change in a flight? CG can travel, right. So this can change, and that will have an effect on the slope of this curve, isn't it, right. So if you talk about this slope, what does it mean? Where is CG lying? If we have fixed the tail, no, nothing else we are going to change here, right. We arrived at this slope using the fact that Cg is lying after the aerodynamic center of the wing, right. So, I can say that right. Now, let us start moving this Cg. Cg is of course going to have an effect on also the tail arm length, right. This Lt is also going to change if you start changing the Cg, right. Not only this distance x Cg minus x AC, right, but this Lt is also going to change because of the Cg travel. Okay. So, let us look at this curve. What will happen when the Cg travels? The slope will start changing, right. Which side you think it is going to be more stable? Let us say I have this Cg here right now, okay. I move the Cg closer to the tail, you will have lesser stability because the wing is having a destabilizing effect, right, and that destabilizing effect will be more, right, if I move this Cg forward towards the tail, right. So, there will be a point, so this curve will start now changing the slope. So, this is more stable, right, everybody agrees with this. This is more stable than this, right, and this will be more stable than this, right. So, you are changing Cg and now you see that the slope of this curve is changing, right. So, there will be one point at which this curve will look like this, right, it will become flat. And what is the Cm alpha for this flat curve? 0, right. So, Cm alpha becomes 0 at this point, right, and this I have achieved only by moving the Cg, right. It is a fact that Cg is going to move because we have fuel on the aircraft which is going to be depleting, right, and you can also there are also passengers moving on the airplane, but we will not bother about that. But one thing is sure that fuel is going to get depleted, right, and what else? You can also have something on the aircraft which you might want to release, right, missiles, or you can drop tanks, right. So, you have fuel tanks, when the fuel is over you want to drop the tank, right. So, that is also going to change the Cg, right. So, there is clearly one point, right, and that is the location of the Cg at which the Cm alpha becomes 0. You know what is that point called? Neutral point of the okay. So, Cg location where Cm alpha becomes 0 is called the neutral point of the aircraft. If you move your CG beyond this point, then what happens? The slope will look something like this. So, Cm alpha curve is positive. Right. So, clearly we have to also ensure that this CG is lying ahead of the neutral point, right. So, that will be another criteria. Okay. So, we already have two conditions that have to be met. Cm naught should be positive, and this slope should be negative. On top of that, you should have your CG ahead of the neutral point, right. So, x CG must be less than, right. From the definition of this neutral point, Cm alpha has to be 0. So, you want to give it any other name? What do you call that point about which there is no change in pitching moment with respect to change in angle of attack? Aerodynamic center, right. So, neutral point location on the airplane is also the aerodynamic center for the whole airplane, right. So, how do you find an expression for x NP here? Set this Cm alpha to 0, right, and that is the point where this CG becomes NP, right. So, let us try to get the expression, and this is for stick fixed case. We are still looking at stick fixed static stability, right. And thus when we will call this neutral point stick fixed neutral point. So, this Cm alpha is 0, and that is the point when CG becomes CG becomes the location of the neutral point when Cm alpha becomes 0. So, you have right. Okay. So, we have found so this location is fixed, right, x AC of the wing, and we are measuring all the distances from the wing leading edge. So, we will call this as 0 and this is your XSCW. Okay, so let's draw a line here, right, which is the location of the neutral point on the airplane. So this is like a stability boundary, right. If your CG is lying ahead of this, then the aircraft is statically stable in pitch, right. If CG goes behind this, then what happens? The aircraft will become unstable in pitch, right. So you have to ensure that your aircraft is having your CG lying ahead of the neutral point all the time, right. Okay. So that is where there is a requirement for this distance, which is called static. So every airplane, conventional airplane, should have this static margin, which is 5% of the mean aerodynamic chord of the wing, right. So when you are designing your aircraft, you should have static margin which is 5% of C bar, right. So we will stop at this point.